Okay, so hi everyone. My name is Jack Koenig. I am formerly a Berkeley graduate student and now a software engineer at SiFive. As introduction said, I am a maintainer on the Chisel3 and FIRRTL projects, and so I'm just here to kind of talk about tools. Usually SiFive talks about chips, but that's not my area of expertise, so I'm going to talk kind of about the open source tool infrastructure that we use and have been building and that lots of people are contributing to. So usually the first question whenever I try to tell someone about Chisel is why? Like, why? Like they will go look at Rocketship, they'll open a random Scala file, and they're like, what is this? Why are you doing this? This doesn't make any sense to me. And the real answer goes back to kind of where RISC-V started, and it was so this, a group of people about this size could build real chips. This picture I think is from Hot Chips 2014. You'll notice I'm not in that picture. I became a graduate student like a week later. And that was also probably like 2 weeks before ORConf when Kirsta came and talked about RISC-V here for the first time. But it was so, a group of people, maybe 10-ish graduate students could build lots and lots of chips. So these are the chips developed, that have been taped out by the research group at Berkeley. Notice that this is kept up. SiFive was started, is this the pointer part? So SiFive started kind of around here. And notice that none of these chips are SiFive chips. This is all just Berkeley. And it's, the older generation has graduated, started companies, done whatever, and now, many students are still working on this stuff. So, okay, there's a little bit of motivation, so now you might be wondering how. Or, maybe a lot of people here are rock star engineers and can do this kind of stuff. We thought that we needed better tools in order to do this kind of work. So our approach is agile hardware design. So for those in the software world, it's like a hot term. And I think, to kind of get past, Scrum and whatever terms that we don't actually really apply, it's really kind of about changing from the waterfall model. So traditionally in hardware, you have this long, 2 to 4, 5 year process where you start out by doing performance modeling, and then you write a big, 100-page specification that you throw over the wall to your RTL engineers. They implement it. Your verification team starts up about halfway through RTL design, and they spend a few years making sure that it more or less works, and then you tape it out. And hopefully you only have to tape it out once. Probably not. Often doesn't work. Tape it out again. So the whole problem here is that developing hardware is hard, and so to manage risk, this whole development flow came about. But the thing is that, and to develop hardware, you do that. Like I mentioned, the design space exploration, RTL development, verification, did we build the thing right, and validation, did we actually build the right thing? I'm going to get back to that last point in a minute. And the issue is when you only have a handful of graduate students, you can't afford to do that. Like, they don't have time. And so this is all about attacking the NRE costs. It costs a lot of money in engineering time to build chips, and so can we make that cheaper? In order to do that, we need a faster design cycle, and designers to do that, designers need to be more productive. So you need to be able to do more with less code, leverage libraries, and write reusable code. And so there on the right is kind of this is the agile hardware design flow that we have proposed and that we use. So on the inside, you do C++, and you do a lot of FPGA emulation, and then as you go further and further out, things take longer and cost more money, but you hope that by optimizing the inner loop, you can get more done. And so how do we do this? How do we speed things up? Well, one of the big ways is parameterization. If you design something and then you want to change it, that can be a problem. So for example, like imagine you have this simple core, caches, FPU, and then your boss comes to you and says, hey, can you make the Dcache bigger? That's a type of parameterization. Or can you make floating point optional? Or can you turn off cache coherence, right? So some of these you may be able to do. The standard Verilog parameter system lets you do some of these things. Like you can parameterize bit widths, and System Verilog has extended this a bit. But when you think about something like turning off cache coherence, that has such cross-cutting implications that it's a pretty hard thing to do. It's a pretty hard thing to express with normal HDL parameterization systems. So the normal way you do it, you start writing Verilog. Then you're like, OK, I can't quite do what I want to do with that. So then you will kind of start a common thing that a lot of companies do is they'll write Perl scripts that concatenate Verilog strings together, but at least it's a little more abstract. But one of the big problems with this is the metaprogramming languages and hosted language are different, so you'll generate the string and your program ran fine, and then you run Verilator or VCS or some simulator, and you get a really hard to debug error, and you have to go back and figure out what went wrong. The problems are found later, and this is one that we think is very important. Perl and Python are not statically typed, which leads to errors coming up later. Of course, you can add all the checking, and so if you do that well, then it can turn out pretty good. But in general, we find that type safety tends to help us be more productive. So what is Chisel? Chisel is a hardware. We call it a hardware construction language. We call it a construction language because fundamentally it's different than what you do with Verilog. So you think about behavioral Verilog. Behavioral Verilog is kind of like software that gets synthesized. It's just very restricted such that tools know how to deal with it. Chisel is not like that. It's a domain-specific language where the domain is digital design, and I'm adding that little caveat or that point because now DSLs are very popular in software and getting popular in hardware where if you have something like Halide and you can write your vision project in such a way that the compiler can figure out how to make efficient hardware, that works pretty well. But this is not that. It's just the basic primitives of designing digital hardware like registers, muxes, and wires, and then you write a Scala program that combines them and generates your hardware. Scala is a language. It's a object-oriented and functional programming language that has parameterized types and static typing. It's a very powerful language in which to do your digital design. And the metaprogramming language and the hardware construction language are the same, that the registers and muxes are like objects, they're classes and objects in Scala. So if you have an issue with the design, then it should error in Scala. It should never make it to the actual Verilog. And if it doesn't error and you're using Chisel, I'm sorry, that's a bug. You should let me know. And really, an important thing that I think is not communicated all the time when we talk about Chisel is that it's intended as a platform upon which to build higher level abstraction. It's not intended to be the end in itself. And I'll talk more about that in a minute. And I just want to shout out to, there's several other people who are presenting on similar things. And so I think Spinal will be the next talk. And it's also embedded in Scala. There's Clash. And I'm not sure how to pronounce it, Paiha. But a lot of these ideas other people are working on them as well. And so the basic concept of writing a program to generate your hardware is kind of an approach that we think makes designers much more productive. Okay, so now I'm going to talk about decoupling design from implementation. So say you have your design and you have some SRAMs. And your boss comes and says, hey, can you punch the SRAM ports out through the top? And you're like, well, sorry. We're not actually sure what the module hierarchy is going to be, and we may not know how many SRAMs are going through various modules, and this is a lot of work for me to do. Can you wait a while before we do this? And furthermore, maybe the SRAM config needs to change. Maybe you ran your memory compiler and you realize that those 8 by 256 SRAMs are not as good as the 256 by 8 SRAMs. And when you change stuff like that, it has massive implications when you're trying to do stuff like this. So the problem is that there are things you need to do in the hardware that are orthogonal from the design. And if you pollute your design with these things, then that makes it difficult to target multiple backends or to run on FPGAs and an ASICs or multiple FPGAs and multiple ASIC technologies. And really, this comes down to kind of a software concept that we're applying here, which is like the separation of concerns. You have your design, your logical description of what you want the chip to do, and you have your implementation, which is the actual technology that you're trying to target. And so the traditional approach is you just do it manually. And when you need to change it, you Control-C, Control-V, and do it again manually. There are some tools that people have developed that run on Verilog, PyVerilog. I don't actually know how used it is, but whenever I Google this, that one comes up a lot. And so that can help with some of the mechanical work, and that is, that's a similar approach. It's a bit more abstract. You can write your own custom tool. But in practice, these things tend to be brittle. The Verilog is a very large language, and systems like Verilog only made it bigger. And so the things, whenever you see, it's a lot of work to get a normal system Verilog design to work on Verilator, despite all of its features. And that's just because the specification is so large. There's various degrees of implementation. So you may write a tool that works on some part of Verilog, and then you add a new feature, and it just breaks. And so our idea here was to borrow good ideas from software and build a compiler. So LLVM has been pretty cool. A pretty cool technique for helping people write, customizations of their software, specialized things, specialized for different, different ISAs and even microarchitectures. And so our thought here was let's try and build a hardware stack where rather than different ISAs, we're talking about different platforms like simulation, FPGA emulation, and ASICs. And so back with Chisel 2, it was kind of this monolithic structure that was hard to do customization on. So we decided to replace that with a leaner front end the Chisel front end, which we compare kind of to Clang, and then FIRRTL, which we are proposing as the kind of the compiler framework. And so FIRRTL is a flexible intermediate representation for RTL. You have a front end that parses and translates the source into an intermediate representation. You apply lowering transforms. So FIRRTL has some higher level constructs, high-ish. It's not a generator language. It's still intermediate representation, but some higher level constructs that you rewrite to simpler, more structural form. A backend that can emit it, custom transformations to make your platform-specific changes without having to modify your RTL, and importantly, that are shareable across multiple designs, and you can compose them together. So we have a paper in ICCAD from last year. If you're interested, you should check that out. And most custom transforms operate on low FIRRTL, which is just because it's a simpler set of things that makes it easier to, you don't have to handle as many features. It's a very restricted AST. And the whole goal here is to kind of build an ecosystem where we have FIRRTL hopefully as this middle compiler, and you can have lots of different front ends, kind of like lots of things compile to LLVM. So we have Chisel3, we have a Verilog work in progress using Yosys. We have lots of custom transforms, some done by Berkeley SiFive, some done by Intel actually, and other outside groups have written some transformations. And you can kind of see the kind of things that you can do, and then it can emit. So FIRRTL just emits Verilog, but by using Verilator, we can run C++ simulations. You can obviously use your regular Verilog simulator, and we have a Scala interpreter as well. But kind of what I'm getting at now, because some of this has been presented before, is trying to apply higher level abstractions on top of all of these things. In my area, mainly Chisel, but who knows what other platforms could apply the same techniques, or maybe somehow we could interoperate. And so now I'm going to talk a bit about parameterization plus plus. So Chisel only provides parameterization insofar as you can write whatever Scala you want. That's really useful, but now what? Now I actually need to build a chip. So say you have this design, you have, I don't know why 3 cores, I guess that's what fit. You have a crossbar and you've got some devices, okay? And then your manager comes to you and says, hey, can you add a UART? You're like, why did you not tell me this? I don't know, when we were doing this design 2 years ago or whenever. And it's kind of a really difficult thing to do, and that's why we have come up with this thing called diplomacy, where you look at these in a logical way instead of a structural way, and it allows you to express this in such a way that it can generate all the difficult parts. It can, when you add that extra UART, oops, I hit the wrong wall. When you add that UART, it can increase the width of the address field or whatever is necessary all the way through the design. Not to mention, it can provide more important information. So many parameters in the SoC are only known once you know the top topology, right? If you add a device that needs physical memory protection, you need to know that in your core or in your cache, wherever you have that unit. But the problem is these things may be very far apart, and so having to, from the top down, tell them all what to do, it complicates the design and it adds things that you don't really care about when you're designing that one thing. All you care about is if somebody needs this, I'll instantiate it. Otherwise, I won't. And so, that's a crossbar when it comes to address decoding. You have to know who is on what address space in order to generate the crossbar. And it's kind of a pain if you have to kind of demand that from the top down. And I already mentioned this one, but physical memory protection or physical memory attributes, you only know that based on what devices you have actually attached. So how do you build this abstraction without having to work, so that you can do this without having to pollute your design with all these concerns? Well, what you could do is just rewrite the crossbar every time. Or more likely, what a lot of people do, you could write or buy a crossbar generator or a knock generator. And that is an approach that is much closer and is a lot better than rewriting your crossbar. But it may work for the crossbar, but what about for the physical memory protection? You still have to propagate that to all these different places. And so that's where diplomacy comes in. So diplomacy is an abstraction built on top of Chisel. It is not Chisel. It is a Scala library. Now, it tends to be kind of coupled to it, but the basic concepts here can be applied anywhere. It provides this known abstraction such that you can separate the logic from the logical layout of your thing from the actual module hierarchy. And there's 2 phases to diplomacy: negotiation and elaboration. Negotiation is where the graph is created, and you can connect nodes together. Elaboration is when you take that logical view constructed in diplomacy and then actually say, okay, now elaborate. you can imagine that any generator could be that elaboration. It doesn't have to be Chisel, but that's the current implementation. And a little bit more about negotiation. This is kind of the part that is like really different from other parameterization systems that we've used, at least, is that one set of parameters flows outward. So from the top down, you may be kind of describing the basic description of what you want, where you say, I want SPI, I want UART, I want this AXI port for memory, all these things. And one set of parameters flows back, where when you plot down that UART, it might say, I know how to speak AXI just fine, but I can only have a 32-bit bus swap interface. Or maybe it can have a range of interfaces that it allows. And so you can add, and then adapters can also modify parameters. And so then any module can place requirements on it, such that it's more of a global problem to figure out what we're building than it is a top-down thing. So what kind of parameters? There's kind of a lot here, and I'm going slower than I should be, so I'm going to kind of just go through them fairly quickly. But cardinality of how many things are connected from the master side, from the source or the sink side. Properties that govern regions, like physical memory protection, address ranges, behavior on particular regions, like if it's modifiable, executable, cacheable, all these types of things that are really complicated when you're doing the uncore or when you're doing any of that. And the idea here is you abstract that all away so that when you want to add something to this system, you just describe what it needs to know and what's necessary, and the diplomacy will do the rest. So here's an actual graph that you can generate with Rocketship. And these are all long. That's kind of a tile link thing. That's not really the point of this talk. But the point here is we've got a few big pieces. We've got a tile. We've got AXI4 to tile link AXI4, and we've got all our peripherals. And the thing is that, way over here on these peripherals, information is needed in the tile when it comes to physical memory protection, or to the address ranges that these peripherals are using. And so what diplomacy does is it just makes all of that really easy to do. And so now I'll talk about one more system that we have been building and using. This one is new. So diplomacy has been presented before, but I don't think this one has. So we're talking here about parameterization, but also decoupling designs from implementation. So previously we talked about decoupling designs. We talked about abstraction. So this is kind of about combining them. So you've got your design, and your boss says, hey, can you run this on a VC707? And you say, sure thing. I will take the design, wrap it up in a wrapper, Verilog. I'm also going to write the constraint files and all of these things. And it runs. It's great. Everyone's happy. And then your boss says, hey, what about a VC118? And you're like, OK, sure, I'll do it again. And so you do. And notice that they're a bit different. Even though these are from the same vendor, there are a lot of things that are different between them, and it's a pain to deal with. And then your boss says, hey, what about this other vendor's FPGA? And you're like, seriously? I finally abstracted some of this out, and we could share, and now we can't anymore. Well, I'm not very happy about that. The problem is that every FPGA, every design requires an a wrapper for every FPGA. If you only have a couple designs and a couple of FPGAs, that's OK. But what we're interested in is generators with lots of designs and hopefully lots of different FPGAs. And this leads to a pretty large cross product of things that you have to do if you want to do this. You need more than just a wrapper. You need the constraints. Traditional approach, and this is what pretty much everyone does, is you do it manually. Or you artificially restrict how many platforms you can run on because it's a pain to make it work. You can use scripts to generate bits and pieces and then manually write the rest. And maybe if you're using Xilinx, I know that they have a GUI. I don't know if anyone else does. You can use that, but that still work for every single one of these points. So that's where FPGA shells comes in. It provides a notion of shells and overlays, where a shell is the interface for an FPGA, and the overlay is a widget or I/O provided by a particular shell. There's no negotiation, so this isn't really diplomatic. This is more the design says, here are the resources I need to run on an FPGA. And the interface says, here are the resources available on your FPGA. The design chooses, and the shells and overlays use object-oriented programming so that you can decouple that interface. So you can write, if your design requires DDR, if your design requires a UART, all these different things, it's built into the type system whether or not those things are available. And so when you run it, Scala compilation will tell you whether or not this will actually work. And of course, not all designs map to all FPGAs. So I mentioned a cross product. It's not really fully populated, but it's still kind of a pain to deal with. And additionally, where I'm talking about decoupling implementation, the FPGA shells also generate the constraint files. So when you want to, if you want to add a new FPGA to your flow or to FPGA shells, you just implement the APIs, and then the rest will just work. And so that's it. This is my last slide, is a call, if you're interested, get involved. We have the upcoming Chisel Community Conference, November 13th to 14th in Berkeley, California. The submission deadline was last week, but as with almost every submission deadline, it got extended. And so it's actually due tonight Pacific time, which is 9 a.m. tomorrow. So if you want to submit, all it is an abstract. We'd love to have your submission. The Chisel Bootcamp is not an event, although that sounds like one. It's actually kind of like educational materials, and it runs in a Jupyter notebook. And the idea is it's mainly built for hardware designers, and it introduces Scala and Chisel constructs as you go. And we have Stack Overflow for Chisel and Rocket Ship and mailing lists. I have the Chisel ones on here. So that's it. Open up for questions.
Thank you very much. Questions?
Hi. So, okay, there's a lot of different higher level abstraction HDLs or HCLs, and I think FIRRTL is a very good thing because in theory you could take all these mygen and myHDL and all things and compile down to FIRRTL, but after that you need to go to Verilog and you lose a lot of annotations. For example, if you wanted to attach debug probes, you just have big netlist basically. So is there any effort of putting FIRRTL directly into the EDA tools or any other IR? Because I'm screaming for an IR inside the tools. I think we need that.
If the vendors would, or open source tools would support it, that would be great. Because you're right. I mean, we use Verilog as essentially another IR, if you will. Like if you've tried to read FIRRTL generated Verilog, you've probably complained because it's nasty, and it is because it's really kind of an interchange. And so we have done a lot of work to interoperate with existing tools, like we generate things for those tools. But we talk to the vendors and we always encourage them to do this, and maybe as more people use this, they will. But to my knowledge, there is no plan at the moment.
Thank you.
Dan.
All right, let me try and ask 2 quick questions here. The first one is, does Chisel have any support for formal verification constructs?
So the Chisel itself does not. The idea still being that you can build the abstractions on top of it. So at SiFive, we are doing some formal verification using Chisel, but it's all it's still a work in progress. So I would say there's not like a good library for it, but ideally there would be.
Okay, that's question number 1. Question number 2, having built my own crossbar generator, those things are kind of fun. The one thing that's gotten me in a lot of trouble, though, is clocks. When you have a particular item that uses one clock or a peripheral and another peripheral that uses another clock, and perhaps the third peripheral uses the first clock, how do you handle your clock generation facility in a way that maintains all of the diplomacy you started with?
So this is, I'm only vaguely familiar with how this all works, but clocks are a first-class feature in diplomacy, and understanding clock crossings are a part of it. I don't know if I can go back fast enough, but in that diagram, oh my goodness, this is the problem with animations. In this diagram, if you look in the middle here, oh no, this one didn't have it. Maybe it's in my extra slides. Let me go the other way. But we have clock crossings all over the place in our diplomatic graphs. So that's the short answer. If you want a more detailed answer, we can talk offline, because I'm probably going to have to ping some people to know the answer.
So that's inserting clock crossings. I was actually asking about the creation of the clocks in the first place via PLLs, and particularly with the FPGAs, you want to create multiple clocks with a single PLL unit sort of thing.
So FPGA shells handles a lot of that. That's not an aspect of diplomacy, but the way FPGA shells works is when you ask for a clock or different clocks with different relationships, it will use the PLLs and other resources available on the FPGA to give them to you.
Thank you.
Thanks. Tim.
So frequently you have a bunch of peripherals and other stuff already written in something like Verilog. Mm-hmm. How can you integrate your existing stuff into something like diplomacy? Is it a all or nothing type approach, or is there a way to integrate your existing stuff?
That's a great question. So we have support for black boxes, so Verilog black boxes. So you can wrap your existing Verilog IP in kind of a Scala shell that provides the diplomatic interface and drop your Verilog in as an instance. And we do have support for basic Verilog parameters in the black boxes that we can support. But at least that aspect of it would work fine. You would just have to write you'd have to write the diplomatic part in Scala, because that's the only current implementation. But otherwise, your Verilog is fine. Did that answer? OK.
Okay. All right.
I have just a quick question. What about also concerning the verification, DFT, clock gating, and also power domains? Do you deal with this?
So for DFT, we have not done any work in FIRRTL yet. One of the big problems with DFT, as many of you are aware, is that it tends to be fairly closely tied to the vendor stuff. So for now, building SiFive chips, we use vendor DFT. Sorry, you asked about clock gating. I don't think we have not built the right abstractions for it yet, but you can do clock gating in Chisel. I mean, you have the ability to express that if you want. And power gating, we have been talking about that because we recognize there's a lot of additional stuff you need to generate when you do power gating. I know there's some work going on at Berkeley on this type of stuff, but I'm not super familiar with what they're doing.
Okay, let's thank the speaker again.